To start this webinar on genomics and machine learning, all you need to know about the GARD technology for in vitro sensitization testing, I would like to present Dr. Andy Forrerud, our scientific liaison and co-developer of the GARD platform. Andy has been part of the development of GARD during his PhD, and hence he has a deep knowledge of each step of it. So please feel welcome, everyone, and I give the word to you, Andy Forrerud.
So thank you very much, Hanna, for that introduction. And of course, I would also like to take the opportunity to welcome everyone to today's webinar. So I'm very glad to see that so many are interested in our technology. So as Hanna also said, this will be the first webinar in a series of webinars that we're going to have this year. So the main focus of this is to give you a brief introduction to SenzaGen and to the GARD assay, and I will try to describe how we can use a combination of genomics and machine learning to actually create next generation's in vitro testing platform for assessment of chemical sensitizers. So before I go into the specific details of our strategy, I would like to give you a brief introduction to our company. So at SenzaGen, we were founded in 2010 as a spin-out from Lund University, and we today comprise a highly multidisciplinary team of 20 employees. So our business model is quite simple. We will continue to develop new in vitro assays, and then we transfer our technology to different CRO partners that will do the routine testing of our chemicals. So our lead product today is GARD, which stands for Genomic Allergen Rapid Detection, which is a state-of-the-art testing platform for assessment of chemical sensitizers. So this platform has today generated 3 readily available assays. So we have the GARD skin assay and the GARD potency assay, which can be used for hazard assessment and also potency assessment of skin sensing chemicals. And we also have now the GARD air assay that can be used for identification of respiratory sensitizing chemicals. So we are a very research-oriented company. We continue to develop new assays, and we of course also work with the applications that we already have available. So today we can offer testing of slightly more complex samples such as UVCBs and natural extracts. So today we are now also traded on the Nasdaq First North. So when we work within the field of predictive toxicology, our ambition is of course to translate a very complex biological endpoint into a tool that we can later use for safety assessment. So of course we want our assays to have a very high predictive performance. We want them to be simple to perform, and also given the current paradigm shift to move away from animal model, we of course want our assays to be performed in vitro. But at least conceptually, there has existed a trade-off behind the simplicity of the assay and the informational content the assay generates, on which we can base our final decisions. So of course the animal models has traditionally provided a lot of mechanistic data, and the in vitro assays, they often are very simple to perform. They have a simple workflow, but they often measure 1 or 2 biomarkers and provide very little mechanistic information. So the ambition with the GARD assay was basically to eliminate this trade-off and develop an in vitro assay with a simple protocol, but yet provide sufficient information for the end user to actually be able to trust the result. So the problem with constructing a too simple model that are often based on 1 or 2 biomarker is that they normally fail to actually capture all the important events in the endpoints that you try to predict. But if you start to add biomarkers to your readout, you can start to build a view that better represents the underlying complexity. And in the end, you will of course like to see the full picture. So the same concept can be shown also in a perhaps more relevant context. If we look at the model in X and Y coordinates, so this model is based on only 2 biomarkers. And as you can see, the information that they contain is not sufficient to actually distinguish the sensitizers and the non-sensitizer. But if you start to add other relevant biomarkers, you can you can build a model that better capture all the underlying complexity, and then you can start to see a separation between the sensitizers and the non-sensitizers. And this transfer from single data point towards biomarker signature with a higher informational content actually forms the basis of the GARD assay. So what I really would like to emphasize in this presentation is that the GARD assay is not actually one single assay, but it's rather a testing platform on which you can base a number of different toxicological endpoints. So all the assays that we have available today, they share the same common structure. So they comprise of a biological system, a relevant biological system. They comprise of a training data that is used to actually find the genomic biomarker signature, which comprise the relevant genes that we look at in our biological system. And on top of that, we also have a prediction model that is based on pattern recognition and machine learning. So I would like to go into these different modules a bit more in details later on in this presentation. So the GARD assay currently comprises of three different assays. So as I said, we have the GARD skin assay for hazard assessment of skin sensitizers. We have the GARD potency assay, which is capable of classifying chemicals according to the CLP potency, so it can distinguish strong and weak sensitizers. And we also have the GARD air assay for identification of respiratory sensitizing chemicals. So as you can see from these slides, all of the applications in the GARD platform, they are based on a set of different biomarkers and not only on single data points. So, of course, all the assays that we have, they can be used on their own. They can be used individually to inform on a specific toxicological endpoint, but they can also be used in a combination to provide a more thorough risk assessment of your compound. So this slide is just basically to show how you can combine the assays that we have in order to test if your specific compound is a non-sensitizer, if it's a respiratory sensitizer, if it's a skin sensitizer, or if it's both a skin and respiratory sensitizer. And of course, if you have identified a compound as a skin sensitizer, you can then further subclassify it if it's a strong and weak sensitizer in our GARD potency model. So I would like to continue this presentation now by describing the different modules in the GARD system. So we believe that one of the most important steps, and it's also the first step for construction of a mechanistically relevant model, is of course to find a biological system that are capable of reflecting the endpoint that you try to predict. So for skin sensitization, which was essentially the first endpoint that we were looking at, I mean, the mechanism of how a certain chemical give rise to the adverse effect, they are quite well known today. And I'm quite confident I don't have to educate this audience in those specific details because you probably know those really well. But I would just like to briefly summarize the key events in this process. So first of all, you have the penetration of the chemicals through the skin, and then it will interact with endogenous proteins to form a hapten protein complex. So these hapten protein complex will then be recognized by dendritic cells. So in response to different type of inflammatory mediators, so they can be generated either by keratinocytes or also, of course, by the dendritic cells themselves. Dendritic cells will migrate to the lymph node where they activate allergen-specific T cells. So this is essentially the first part of the sensitization reaction, and this is what is referred to the sensitization or priming of the immune response. So every time that you're then exposed to the same chemical, you will have a T cell proliferation and eventually give rise to allergic contact dermatitis. So if we look at only the endpoint for skin sensitization, dendritic cells, they are of course a relevant cellular target because they are the cells that bridge the innate immune system with the adaptive immune system, and they are very important in order to give rise to the adverse outcome. So a relevant question here is now, of course, how do this translate to the situation of respiratory sensitization? And I think we can actually use the adverse outcome pathway for skin sensitization as a point of departure to explain this. So the adverse outcome pathway is basically a structured way of organizing the information I had in my previous slide. So it explains the key events that is required for developing the adverse outcome, starting with the molecular initiating event of the hapten formation, and goes through all the important key events all the way to development of allergic contact dermatitis. So for respiratory sensitization, I mean, this is the adverse outcome pathway for skin sensitization. So if we look at respiratory sensitization, there's not as much information available. We simply don't know exactly how respiratory sensitization develops. But last year, there was a publication by Dr. Ian Kimber, who described a hybrid AOP for skin and respiratory sensitization. And as you can see, the respiratory and skin sensitization, they essentially share exactly the same key events, but they will in the end give rise to a different adverse outcome. So skin sensitizers cause allergic contact dermatitis, and respiratory sensitizers frequently cause occupational asthma. And his conclusion was essentially that one of the main mechanistic difference is not in the different key event, but is rather in the fine details in this mechanism, such as, for example, that skin sensitization is driven by a T helper 1 response and cytotoxic T cells, and occupational asthma is driven rather by a T helper 2 response. So based on this, we believe that dendritic cells is a very good model, also capable of reflecting the endpoint of respiratory sensitization, because dendritic cells, they are the cells that are responsible for driving the polarization of T cells into either a T helper 1 response that is responsible for skin sensitization, or a T helper 2 response that are associated with the development of respiratory sensitization. So this actually forms a very good basis for the development of a system that are capable of discriminating between skin and respiratory sensitization. And also at this time, I would like to address another misunderstanding regarding respiratory sensitization, because it has been shown that respiratory sensitization can actually be triggered through the skin exposure. So that means that you don't have to design a predictive system that are based on cells that are only present in the respiratory tract. And of course, you don't need to have an inhalation exposure in that sense neither. So the cells that forms the core of the GARD assay is a dendritic cell line from humans that is called Senza cells. So this cell line is very similar to human primary dendritic cells. So they are capable of taking up and process antigen on MHC class 1 and class 2 complex, and also on the CD1D. And they respond to pro-inflammatory measures by upregulating co-stimulatory molecules such as CD80 and CD86, which is of course a prerequisite for activation of T cells. And also what's really important in this sense is that they contain the functional elements that are required for polarizing the T cell response into either a T helper 1 response or a T helper 2 response. So, of course, when we now have defined the cellular system that we would like to use in our assay, we of course need to find a way to see how the cells react to external stimuli. So we know that dendritic cells react in many different ways when they're exposed to a sensitizer. So first of all, they have different type of receptor for recognizing foreign substances. They have different type of, that may in turn activate different type of activation self-defense mechanism. And you might also have different cellular stress response, such as, for example, oxidative stress. And they may also, of course, upregulate different type of receptors that allow them to activate the adaptive immune system. So the big question here is now, how do we measure all these events at the same time? So looking at the central dogma of central biology, we know that all of these events are carried out by proteins, which in turn is regulated by the transcription of DNA. So we believe that measuring the transcriptome of the cells is a very good way of get a complete view of how these cells actually react when they are exposed to a sensitizer. So based on this, we early on hypothesized when we developed our assays that it should be possible to identify new genes in dendritic cells that are differentially regulated dependent on whether they were stimulated with a non-sensitizer, a respiratory sensitizer, or a skin sensitizer. And of course, we could identify those specific subset of genes. We could also use them as a predictive tool. So I would like to start with the first thing here. How do we actually identify the differentially regulated genes in the cells? So in order to do that, we need to move on to the second module here, which is the training data set. So the definition of a training data set is basically a set of chemicals with known expected outcome. So they should be well characterized in the scientific literature, and we should know what kind of response that they normally induce in humans. So the other thing that we actually look for is, of course, that we want the chemicals to cover a large chemical space. So this essentially means that in terms of sensitization, we would like to have a good balance between the different reactivity domains, but we also want to have the different industrial applications represented in our training data set, because this would in the end allow us to study different type of mode of action. We can see how different type of chemicals interact with our cells, and I will show you later on how this will result in a broad applicability domain. So after we have identified the chemicals in our training data set, we of course use them to stimulate our dendritic cells, our Senza cells. So after we have stimulated the cells with each of the compounds in the training data set, we simply extract all the RNAs from the cells, and we measure the complete transcriptome of the cells using an Affymetric platform. So for each chemical, we measured 29,000 genes per sample. So this will generate a huge data set for us. And that will, of course, lead us to the next module in our assay development step here, which is the identification of the genomic biomarker signature based on how the compounds in the training data set actually interact with our biological system. So in order to identify our predictive biomarker signature, we use a data-driven approach where we start with all the 29,000 genes for each chemical, and we identify those genes that are differentially regulated between the group of non-sensitizers and sensitizers. So basically what you see in this figure is the 200 genes in the GARD prediction signature for skin sensitizers. So this is just examples, but it could equally be the other biomarker signature we have, because the identification process is performed similarly for all the biomarkers that we have. So as you can see here, there's a good separation between the sensitizers and the non-sensitizers in the heat map. And also you have a lot of information here because you know exactly how each chemical interact in this profile. So once we have identified our biomarker signature, our ambition is always to transfer our gene expression measurement from measuring the complete transcriptome of the cells to a more high throughput gene expression platform that measure only the genes in our signature. I mean, the Affymetrics platform that we use in order to identify our biomarker signature is extremely useful because, I mean, you can look at the whole transcriptome of the cells, and then you can reduce the number to only those genes that are highly predictive. But it's the platform is simply not does not fit very well into routine testing because it's very labor intensive, it's very hard to automate, and it has a very, very low sample throughput. So what we do after we have identified our biomarker signature is basically that we transfer the genes to another hybridization-based platform that is called nanostring. So the benefits here are, of course, apparent because we can do the analysis in 22 hours with only 15 minutes hands-on time, and we can simultaneously increase the sample throughput to 384 samples per day. And you can do the analysis directly from total RNA, so you don't need to to prepare any cDNA again. So the technology in nanostring is very simple. So for each gene in your biomarker signature, you need to design a transcript-specific molecular barcode. So each barcode that you have different combinations of fluorescent molecules attached to it. And these different combinations are, of course, then used in order to identify a specific transcript, but also in order to quantify the exact number of copies you have on your barcode. So what we basically did after we have selected this platform is, of course, that we translate all the genes we have in our biomarker signature from the Affymetrix into the nanostring. And we were really careful to be able to match all the Affymetrix data at an exon level to the nanostring probes in order to be able to cover exactly the same splice variant. So this is again the data from GARD skin, the 200 genes that I show you here, but we do exactly the same for the other assays that we have as well. So after that, we basically rerun our complete training data set on the nanostring platform. So what we see here is basically the comparison between the gene expression profile generated on the Affymetrix and also on the nanostring platform. So as you can see in this figure, I mean, we have a very, very similar gene expression measurement on both platforms, and we have a Spearman correlation for each simulation that is between 85 and 90%. So it's a very good correlation between the gene expression measurement measured on the nanostring and the Affymetrix platform when we look at the complete biomarker signature. So, I mean, this makes it, of course, possible to transfer our assays to the nanostring platform, but it also serves as a quality metrics that we can verify the gene expression measurement from Affymetrix on an independent platform. So this, of course, strengthens our case that we measure relevant and fixed immunologically relevant endpoints. So once we have then identified our predictive biomarker signatures, and we have also transferred the biomarker signatures to the nanostring platform, we of course need to move over to a prediction model. So the prediction model basically contains the rules that can look into the traditional or the historical data we have in order to predict the sensitizing properties of our unknown testing substance. So just to briefly remind you where in the process we are. So what we have done now is basically that we have identified the differentially regulated genes in our cell system, and they are what we refer to as the genomic biomarker signature. So now we need to find a way to use these genes as a predictive tool. So in order to do that, we use something that is called pattern recognition and machine learning. And I mean, I often hear a few misconceptions about the concept of machine learning, but the general structure of how this works is actually quite simple. And I would like to describe it a bit more in detail, how it works in the GARD setting. So, I mean, the general idea behind machine learning is similar as a human learn. So humans learn from their past experience. And you can also program a computer to learn from their past experience. And that is basically the definition of machine learning. So I would like to show you a bit how this actually works and how we can train this model in order to classify our novel test substances. So what we need is that the machine actually learns by observing a data set of objects with known expected outcomes, which are, of course, the labels. And this is exactly what we have when we look at our training data, because there we have the gene expression profiles from well-characterized sensitizers and non-sensitizers. And the label here refer to the sensitizer and the non-sensitizer label. So how do we then use this information to train the model to classify novel compounds? So first of all, we use our training data set as input into our machine learning algorithm. So the machine learning algorithm basically learns to discriminate the gene expression profile induced by a sensitizer against those that are induced by a non-sensitizer. So when you then have a new test compound that is unknown, which is here represented by the question mark, and you like to predict to predict the sensitizing properties of this compound, you basically only compare the gene expression profile induced by this compound to the samples in the training data. And that is exactly what the machine learning algorithm do. So in this case, you can see that it's quite a light gene expression signature, which is very similar to the gene expression signature that is induced by the non-sensitizer. So in this case, the compound was classified as a non-sensitizer. But we can, of course, add a more mathematical explanation of how this actually works. So what this actually is, if we can, of course, express our training data. I mean, the heat map we have here can, of course, be expressed as a matrix where you have the gene expression data and you have the number of samples on the rows, and you have also a well-defined class label on those samples. So when you feed the samples into the machine learning algorithm, it becomes nothing less than an optimization problem from a mathematical point of view. So what the machine does here is actually to assign different weights to the different genes with the purpose to optimize the discrimination between sensitizers and a non-sensitizer. So this will lead to a fixed mathematical formula that is never changed. So every time that you will try to feed in some new data in your test data, you will have exactly the same fixed mathematical structure. So when you then should predict your unknown testing substance, you of course have the gene expression data because you have measured that, but you don't have the class label. So you feed this into your fixed mathematical formula, and you will have the machine learning algorithm to predict your class label. So this is basically an overview of how this actually works. So today there is many different machine learning algorithms that are available in the scientific literature. So we decided to work with something that is called support vector machines. So this is quite a simple model to explain. So I will try to do a short explanation of how this actually works by looking at only 3 biomarkers. So here you have the measurement of 3 biomarkers. It's along the X, Z, and Y axis. And you have, of course, your label here because it's the training data. So you have the sensitizers and the non-sensitizers, and you have the gene expression data from 3 biomarkers. So what the SVM actually do is to try to find a hyperplane that best separates the sensitizers and the non-sensitizers based on this information. So what you then have, when you have an unknown test compound, it will be assigned a support vector machine decision value. And this is basically only the distance between this separating hyperplane and the unknown test data. So a positive value will be classified as a sensitizer, a negative value will be classified as a non-sensitizer. So in this specific case, we can see that the compound, the test compound, is above the hyperplane, and it will subsequently be classified as a sensitizer. So even though I only show here for 3 biomarkers, the same ID works perfectly well for 200 biomarkers, but then you need to look in 200 dimension, and that is of course not possible to visualize, but you can still use the same mathematics to describe it. So just to briefly show you how we use this in a real setting. So this is a data from a recent test set that we have. So you have the true sensitizers to the left of the dotted line and the true non-sensitizers to the right, and you have the hyperplane at 0. So all those that are assigned a positive value here is classified as a sensitizer, and the negative ones are classified by the algorithm as a sensitizer. So the reason why we have 3 dots there is because we always test each chemical in triplicate reactions, and we base our final decision on the mean value of this. So having explained now how we do in order to develop our models, I would like now to describe more how we do when we get an unknown testing compound, and we should use this information in our model to inform on specific hazard. So this is just a brief summary of how you can guard your product in only 6 steps. So the first thing we do is basically to screen for cytotoxic effect. We would like to find one input concentration that we should use in our assay. So we typically aim at the concentration of the chemical that induce a relative viability of 90% of the cells. So once we have performed this initial study, we perform our cellular stimulations again at the defined GARD input concentration. We perform a quality control of the cells, and we extract all of the RNA from the cells. So after that, we basically measure the genes in our prediction or our genomic biomarker signature using the nanostring platform. So now we only measure the genes in the specified genomic biomarker signature, and then we use our machine learning algorithm in order to compare the gene expression profile induced by the unknown testing compound to the expression profile induced by the sensitizers and the non-sensitizers in our training data set. So you will have a final classification. If it's above 0, it's classified as a sensitizer, and if it has a negative value, it's classified as a non-sensitizer. So this is basically how we design our assays and how we use them in order to test different compounds. So now I would like to give you a bit more information into the specific assays that we have available. And I would like to start with the GARD skin assay, because this is the first assay we developed, and it's also the data that the model that we have most data available on. So you might recognize this slide. This is exactly the same. To develop this strategy, we use exactly the same strategy as I described previously. So we have the same biological model, and we have a training data set comprising 20 skin sensitizers, 20 non-sensitizers. And again, these are well balanced according to chemical reactivity domain and also to their industrial applications. So we stimulate our cells, and we identify genomic biomarker signatures using our data-driven approach. So this is the same data as I showed previously, is the 200 genes that form the GARD prediction signature for skin sensitization. So on top of that, we add our pattern recognition model. So for all our assays, we highly value transparency. So it's really important for us to publish all the data on our assay development step. And we also published all the genes that we have, because we want our customer, our clients, and we want the scientific community to have access to our information in order to be able to judge on themselves how well this actually works. And that is really important for us. And we have published a complete list of genes for GARD skin in 2 different publications. So this is nothing that is secret. It's all available in the scientific literature. So we have tested the GARD skin, the performance of the GARD skin assay in many different external test data sets. So today we have tested about 207 compounds with an accumulated accuracy of 89%. So all of this data has been published in or are about to be published very soon in peer-reviewed scientific journals. And this is only the data that we have basically generated in-house or together with our collaborators, because I don't want to show our customer data. We have quite a lot of customer data as well, but I don't want to disclose this at this time. So this is the data that we have generated in-house. So based on this data, we have, of course, also would like to push this assay into a formal validation. So we have also now finished a formal validation study that was performed in compliance with OECD guidelines on how to validate non-animal based approaches. So this basically showed a setup of the validation study that we performed. So we performed this validation together with 2 independent laboratories. It was Burleson Research Technologies in the US and also Eurofins in Munich in Germany. So what we basically did was that all of the laboratories were given a subset of 28 chemicals that should be tested in a completely blinded fashion. So none of the laboratory had access to the codes for the chemicals. And this is basically the data from the validation study. So just briefly to remind you how to interpret the data. So the chemicals to the left of the dotted line, they are the true sensitizers, and the compounds to the right is the true non-sensitizers according to reference data. And the positive value is classified as a sensitizer. The negative value is classified as a non-sensitizer. So as you can see from this figure, there is very little variance between the different experiments, but also between the different labs. And the majority of the sensitizers and the non-sensitizers were correctly predicted. So if we should put this in number, we experience a between laboratory reproducibility of 92% and accuracy of 94%. That is very well balanced between the sensitivity of the assay and also the specificity of the assay, which is quite unique for current in vitro tests that are available. So just to briefly remind you again that this is all performed on completely blinded data. So another thing that is of course important to see is how does the GARD assay perform in comparison to other in vitro assays, and of course to the OECD validated approaches and the currently suggested 2 out of 3 integrated testing strategy. So the data I show here is basically a comparison that David Roberts from John Moore University in Liverpool did. So he identified the largest subset of compounds that had been tested both in the GARD assay, but also in the other 3 OECD validated assay. So his overall conclusion was that the GARD assay outperforms all these assays, both on their use on an individual level, but also if they were to be combined into a 2 out of 3 testing strategy. So I guess that one of the most probable explanation to why GARD performed this well is because we do not only cover in our genomic biomarker signature, we do not only measure one specific endpoint, but we measure a whole set of different endpoints that are immunologically relevant to the sensitization reaction. So when we actually look at the specific genes we have in our prediction signature, we can see that they do not only describe one single mode of action, but they are rather involved in a broad spectra of different pathways that are involved in development of skin sensitization. So we, for example, measure the different toll-like receptors, we measure the co-stimulatory molecules, we measure genes that are involved in the cellular stress response, such as the NRF2 pathway, and we also measure a few chemotaxis receptors. So if we try to map the genes in our biomarker signature to the different key events in the adverse outcome pathway, we can see that we measure already CD86, which is the endpoint that is measured in the HCLAT, for example, and we also measure the NRF pathways, which is the endpoint that is measured in keratinosense. So in addition to this, if we continue to characterize the genes that we have in our prediction signature, they actually cover a broad spectrum of the different key events that are represented in the adverse outcome pathway. So this essentially forms an integrated system that can actually be used in order to inform on skin sensitization. So another thing that is quite popular to talk about when you evaluate the performance of different in vitro assay is of course their applicability domain. So this is just to show the number of chemicals that we have tested this far with respect to their different industrial applications. So the numbers that are posted in the bars, they are the number of chemicals in each industrial sector. And the dots on the top are basically how the accuracy varies for the different industrial groups with respect to the mean accuracy of the assay. So we have the mean accuracy at 89%, and you can see how the accuracy does not is not very far away from this measure for any of the groups that we have tested here. So that's a kind of an indicator that we can test many different industrial applications. So by that, I would also like to move over to something that is a bit more blurry, because people often refer to something that is called difficult to test substances. So I think that this actually relates to compounds that has historically been hard to test in different in vitro systems due to different properties of the specific chemicals. So, I mean, one thing that has been suggested is that pre and prohaptens will be really hard to predict in vitro systems because they need some form of activation in order to create the allergens. So if we look at what genes are actually present in our dendritic cell line, we do have a lot of those metabolizing enzymes that are actually capable of converting the prohaptens. I mean, in general, in theory, it should not be any problem for our assay to assay pre and prohaptens. And the other thing that we normally say is difficult to test substances is compounds with a high octanol partition coefficient, or if they have other properties that are will result in very low water solubility in aqueous media. So what I basically did yesterday in order to complement this information, that I'll look into our historical data on pre and prohaptens, and I also looked at the compounds that we have tested with a high log p value. So the high log p value is here defined as a log p value above 6. So this is again only the data that we have generated in-house. We do have a lot more data available also from different customer projects that I'm not about to show here. So, but what you can see generally, and that holds true both for the 8-clat assay and the GARD assay, is that pre and prohapten is in general not an issue for this dendritic cell based assays. And if we look at those compounds with a high log p value, they seems to work quite well also in the GARD assay. So, I mean, this has been pre and prohaptens and compounds with high log p value has been one of the main arguments to actually incorporate 3D based cell models. But I think this slide shows that we can actually test them in the available assays that we have already, such as, for example, I mean, HCLAT for pre and prohaptens, and the GARD assay for compounds with low solubility, and also for pre and prohaptens. So in addition, I would like to briefly show you how we do today in order to test very unpolar compounds such as natural extract and UVCBs. So we know that our cells are compatible with many different type of solvents that have different properties, such as very polar solvents, but also very non-polar solvents. So basically, this is just to show you how we did with one compound that we had that was very, very low water solubility. So we first tried to use DMSO as the solvent, but it was practically impossible to get this compound into solution. And as you can see from the top figure here, it was impossible to have any bioavailability of this compound neither, and the compound was predicted as a non-sensitizer. So when we instead used a combination of less polar solvents, we can actually get this compound into solution, and we could also observe a bioavailability, which is here illustrated by the drop in our relative viability. And as you can see also, when we did the prediction in our model, the compound was correctly classified as a sensitizer. So this is just to show you how we work around with different type of solvents in order to test compounds with very low water solubility. So based on that, I would like to move over to the next applications that we have available, which is our GARD potency signature. So the GARD potency signature is capable of subclassifying chemicals according to the CLP classes, which is strong sensitizers and weak sensitizer. So you might start to recognize this strategy that we use now. So we use the same biological system. On top of that, we use a training data comprising 22 strong sensitizers and 29 weak sensitizers. And we use this information in order to extract a genomic biomarker signature. And this is what I show in the slide to the right. So this comprises of 28 genes. So on top of that, we also, of course, add our prediction model. So as you can see in the heat map, we can actually see that there is many genes that are differentially regulated dependent on the inherent sensitizing properties of the chemicals. So just to compare this to the GARD skin model, we of course have the same setup, but we use another training data set with other labels, and we of course identified another genomic biomarker signature. The other things are similar as to the GARD skin assay. So the intended use of this signature is within a tiered strategy, where you basically identify your skin sensitizers first in the GARD skin assay, and then you further subclassify your compound as strong and weak sensitizers in the GARD potency assay. So with this potency assay, we are also moving towards formal regulatory acceptance. And that is performed in a second phase of our validation study. So this phase basically includes the further subclassification of an additional 30 blinded compounds. And this is basically show the data. And just to remind you that we only subclassify those chemicals that has first been classified as sensitizer in GARD skin. And this is the data that has been submitted to regulatory authorities now as well. So for this tiered approach where we have the non-sensitizers, the strong sensitizers, and the weak sensitizers, we have an accuracy of 82%. So all this data from GARD skin and GARD potency, they have been submitted to regulatory authorities, to the ECVAM, and we are currently waiting for a scientific review and also for a formal approval. So while we are awaiting this, we do have a statement from the European Chemical Agency that it is possible to use the GARD assay in order to, as a point of departure or a weight of evidence, in order to fill your REACH dossier for key event number 3. So the last assay that I would like to show you today is the GARD air assay. For identification of respiratory sensitizing compounds. So I guess that respiratory sensitization people are not as aware of as skin sensitization. So I would just like to briefly give you an introduction to what this actually is. So a respiratory sensitizer is essentially a chemical compound that are capable of inducing an allergic hypersensitivity reaction in the airway, which may eventually give rise to occupational asthma. So from a toxicological perspective, the main problem with this type of substances are that they normally induce positive responses in animal models that are developed to predict skin sensitization. And this is despite the fact that this not often translate to allergic contact dermatitis in humans. So there is a clear distinction between the skin sensitizers and the respiratory sensitizers. And one of the major issues is that there is no validated assay available that are capable of specifically identify respiratory sensitizer. So with the GARD air product that we have, the identification of respiratory sensitization, we were fortunate enough to receive external funding in order to continue work with the development of this model and also to eventually bring this into an industrial application. So we received a lot of funding from the Horizon 2020 project. And I would like to show you the results on how we have now developed this assay. So as you start to recognize now as well, we use the same strategy. We have the biological model, and on top of that, we add a training data set. And this time we, of course, include 10 well-characterized respiratory sensitizing chemicals, and we have 20 non-respiratory sensitizers. And among those non-respiratory sensitizers, we of course also included skin sensitizers because they are very seldom respiratory sensitizers. So from this data, we identified 51 genes that discriminates between the non-respiratory sensitizers and the respiratory sensitizers in our training data. And that is what we refer to as the GARD respiratory prediction signature. So on top of that, we of course use the same prediction model, but the thing that is different from our skin models are that we use another training data set and another genomic biomarker signature. So of course, if we start to characterize the genes that are available in the GARD respiratory prediction signature, we can see that they are indeed also immunologically relevant to the event of respiratory sensitization. So we do have a lot of molecules that are involved in the activation of innate immune responses. And perhaps more importantly, what we found was, of course, also regulation of the TSLP receptor signaling. And this is one of those receptors that are well known to be able to drive the polarization of the T cell response towards a T helper 2 response. And this is, of course, also the main characteristics or the molecular characteristics of occupational asthma. So we have tested this assay also on an external test data set. So this is to show you the first 20 compounds that we tested blindly in this assay. So among these 20 compounds that we tested in this signature, we had an accuracy of 90% and a sensitivity of 100%. So this essentially means that we were able to identify all of the respiratory sensitizers in this assay. So another thing that I would really like to emphasize here is that in this test data set, we also included 8 skin sensitizers. And we can see that 7 of those 8 skin sensitizers were correctly predicted as non-respiratory sensitizers in our assay. So this essentially means that the respiratory sensitization assay is capable of discriminating between skin and respiratory sensitizers in this very limited test data. So at the same time, we of course try to identify novel test compounds to test in our assay, to challenge our assay. And we are currently running through different type of test substances now. So this is basically to show here that regardless of what test set we use, we observe similar accuracies and performance of this assay. So what we currently work on now is basically to perform a ring trial using the same setup as we did on the validation studies that we performed with the GARD skin and the GARD potency assay. So we are currently running this in our external laboratories, and we hope to have this data available in the end of the year. So based on the results that we have generated this far with the GARD air assay, we were also fortunate enough to receive a recommendation from the European Union that we were appointed as an European Union flagship project, because we are addressing a health point that is very relevant from a regulatory perspective. So based on that, I would just briefly like to summarize the data that I've shown you here today. That I think that the GARD assay offers a unique possibility within hazard testing of chemicals. It uses a completely data-driven approach. It has high informational content, and it combines this information with state-of-the-art machine learning approaches. So the GARD skin assay that we have has the highest reported predicted performance, and it's also currently under review for regulatory validation. We have our GARD potency assay, which is capable of subclassifying the sensitizers according to the demands from the regulators as strong and weak sensitizers. And we also have our GARD air application, which is the first in vitro assay that are capable to test or identify respiratory sensitizing chemicals. And what I think is really important is that the technology is available for use already today. So how do I do if I would like to test my substances in the GARD assay? Of course, the first thing you need to do is contact us, and we will be really happy to help you to design an appropriate test strategy. And then you can select which assay you would like to test. If you have information on what vehicles that are appropriate for your specific compound, you can send us that information. Otherwise, we will be happy to test it for you. So the general turnaround time is between 6 and 8 weeks. We require very little sample, so 0.5 grams of solids or 1 milliliter of liquids is definitely sufficient. And we can also do with less. We can adapt the protocol to deal with less amount as well, if that would be a requirement. And then you of course need to select your preferred site of testing. And we today have a lot of we have some CROs partners that are up and running today. So in the US, we have a collaboration with Burleson Research Technologies and also with MB Research Laboratories. And in Europe, we have a CRO partner in Eurofins in Munich. And of course, in addition to that, we do have a global net of distributor that can help you to organize your testing as well. So by that, I would just like to round off this first webinar. So this was basically a general introduction to GARD and to our assays. And as Hannah also said before, we will continue to follow up on this webinar and show more real data and more applications. By that, I would just like to thank you all very much for listening to this webinar, and I will be happy to take any questions that you might have.